Regarding the classical theory of scattering, till now I have provided two videos. In first video on classical theory of scattering, you have seen some basic definitions and basic concepts regarding the scattering theory. And you have seen what is impact parameter, what is angle of scattering, what are uh, differential scattering cross section and total scattering cross section. This was the subject matter of my first video in classical theory of scattering. You have seen actually the expression, or you can say general expression, for the differential scattering cross section in first video. And I have definitely told you, for the further discussion you must remember that expression for differential scattering cross section. And if your aim is to find the total scattering cross section, you simply integrate the differential scattering cross section with respect to the solid angle. Okay. And then in second video on this scattering theory, I have properly discussed the Rutherford scattering theory. And in that video you have seen we have calculated the expression for the angle of scattering, or you can say the relation between the impact parameter and the angle of scattering. Now today our prime aim is to find the scattering cross section in case of Rutherford scattering theory, or you can say Rutherford alpha scattering. Alpha is just an example because the original experiment on this scattering was performed by Rutherford using alpha particles. But now you can perform the same experiment by taking different projectiles. You can take protons or any other positively charged projectiles. Okay. So the sole aim of the today's lecture is to find the scattering cross section of this Rutherford alpha scattering. Okay. As we have seen in the previous lecture, that if we assume that this dot represents the nucleus of our target and an alpha particle having charge plus 2e is projected with an initial kinetic energy, let us say E, from infinitely large distance from the nucleus in the direction, let us say this XO. Then due to Coulombian repulsion, you have seen the alpha particle gets deviated, and this alpha particle actually moves in the Coulombian repulsive force, which is a central force and it is repulsive. So the trajectory followed by the alpha particle shown in this figure XAY. This XAY is actually a hyperbola. We have actually proved this fact in the previous lecture. Okay. And after proving that the trajectory of the alpha particle followed in this during its scattering in this central force field, it is a hyperbola, you have proved that what you have actually found the expression for the impact parameter, and how the impact parameter is related to the angle of scattering. You can see this figure that this XO represents the initial direction of motion of the alpha particle, and this OY represents the final direction after scattering. So the angle, this angle phi, which is angle between the incident direction of alpha particle and its scattered direction, this phi is called angle of scattering. Okay. And when you draw a perpendicular from the center of force, or you can say center of scattering, that is this nucleus, on the line of initial direction of motion, then this then the length of this perpendicular, which is equal to p, this is called impact parameter. Okay. And how this impact parameter P is related to phi we have seen in the second lecture, and how differential scattering cross section is defined and what is expression for it we have seen in the first lecture. So actually if you want to find the scattering cross section of this scattering process, definitely you have to use these two results which we have already studied in the previous lectures. So here I will mention those results directly because you have learned about these in previous lectures, and using those results we will be able to find the differential scattering cross section of this process. Okay, so let us see. I have mentioned here the important two results which will be needed for finding the scattering cross section. You have seen in the second lecture on this scattering theory that this P, which is impact parameter, that is equal to C over E cot phi by 2. Okay, and sigma phi, which this sigma phi is actually also denoted by d sigma by d omega, and this is called differential scattering cross section. Okay, and this is differential scattering cross section. What is this differential scattering cross section, and how this expression which I have mentioned here is obtained? You have seen in the first in my first lecture on this scattering theory, and you have seen that actually this sigma phi is equal to minus P over sine phi dP by d phi. Actually here this minus sign has been imposed as with increase in phi P decreases, or you can say with increase in P phi decreases. So this minus sign has been used. Actually we have derived these two results in the previous lecture, so I have mentioned these two results here directly. Okay, so you can see how easily now we can find the expression for this differential scattering cross section, because already P is known here. Okay, and for finding the expression for sigma phi we need the expression for P. Okay, and this relation also shows the relation between P and phi, and so we can easily find this dP by d phi. So finding the value of dP by d phi and this P, when this will be used in this expression, we will get very easily the expression for the differential scattering cross section. Okay, actually this constant C you have seen in the previous lecture, this is equal to ZE times 2E divided by 4 pi epsilon naught. Actually here this ZE is the charge of nucleus and 2E is the charge of alpha particle. You can say that if instead of alpha particle anyone use another projectile having positive charge, and let us say charge of that projectile is plus a small ZE. Here Z is a number and this plus ZE, where Z is a small z, that represents the charge of the projectile. Then you can write this plus ZE instead of this 2E, because 2E is particularly the charge of alpha particle, but in general if you consider that there is a projectile whose charge is plus ZE, don't confuse this small z with this capital Z. This capital Z is atomic number or number of protons in the nucleus, but this small z is a number in whose multiple the charge of the projectile has been expressed. Okay, so C is equal to this much. Okay, and now as we know the expression for P from which we can find dP by d phi, and then using those values in this expression for sigma phi we can easily find the expression for the differential scattering cross section. And after getting the result for differential scattering cross section we will also see a very important problem. Okay, so let us see how we can calculate this differential scattering cross section. As we have seen that P is equal to this much, that is P equal to C over 2E cot phi by 2. And for getting the result for differential scattering cross section, we must know what is this dP by d phi, because this expression you can see contains dP by d phi. So now let us find dP by d phi. For this we will simply differentiate this expression. But C over 2E is constant, so it is outside of the differential operator. And differential coefficient of cot phi by 2 will be what? That will be minus, I have written here minus 1 by 2 cosec square phi by 2. So dP by d phi is equal to minus C over 4E times cosec square phi by 2. Now let us put the value of this P and dP by d phi in this expression, which is the expression for the differential scattering cross section, and you will, and simplify, you will see the expression for differential scattering cross section is how easily obtained. So as we know, sigma phi, which represents the differential scattering cross section, this is equal to minus P over sine phi times dP by d phi. But you can see P is equal to this much. This is C over 2E times cot phi by 2 and times 1 over sine phi, and dP by d phi. See here, this is minus C over 4E cosec square phi by 2. Okay. Since here is also minus sign, and in this expression already this minus is present previously, so this minus will become plus, and so sigma phi will be equal to C over 2E times cot phi by 2 times 1 over sine phi times C over 4E cosec square phi by 2. Okay. We have substituted the value of P and dP by d phi in this expression. Now let us see. This C times C, this will be C square. 4E times 2E, this is 8E square. Okay. And cot phi by 2, this is cos phi by 2 over sin phi by 2. Now this sin phi can be written as 2 sin phi by 2 into cos phi by 2. Okay. And cosec square phi by 2, this is 1 over sin square phi by 2. Okay. So now this cos phi by 2 and this cos phi by 2 will cancel out, and your result becomes like this. This sigma phi is equal to C square over 4E whole square times 1 over sine 4 pi by 2. Here, as you have seen earlier, that this constant C is equal to this much. This is 2ZE square over 4 pi epsilon naught. So now let us substitute at the place of C this much. And after substituting this value of C, you get sigma phi, which represents the differential scattering cross section. That is what? That is 4Z square E4 over 4 pi epsilon naught whole square times 4E whole square times 1 over sine 4 pi by 2. Okay. This is the well-known expression for the differential scattering, Rutherford scattering, differential scattering cross section. Okay. Now, as I have told you earlier, that since Rutherford has used alpha particle as projectile in his original experiment, but if nowadays the same experiment will be performed, we can use another projectile, but the projectile must be positively charged, because here the Coulombian repulsion is responsible for the scattering. So for this, it is needed that the projectile used in this experiment must be positively charged. So if instead of alpha particle, another positively charged projectile will be used, and if you consider that the charge of that another projectile is plus a small ZE, plus a small, mark this, this is a small z, okay, then the value of the constant C will be what? That will be capital ZE. This is actually charge of the nucleus. Here this capital Z represents the total number of protons inside the nucleus, times a small ZE. This small z represents a number, and a small ze is charge of the projectile, and divided by 4 pi epsilon naught. So in this case, if you want to find the differential scattering cross section, substitute this value of C in this expression. See here. And substituting this, you will get that this sigma phi will be equal to 1 over 16 times a small z into capital Z E squared divided by 4 pi epsilon naught times E whole square times cosec 4 pi by 2. This is the well-known expression for the Rutherford scattering cross section. Okay. Now you can see from this result that the scattering cross section, and you know a scattering cross section actually represents the number of particles scattered per second along the direction phi. Okay. That number of particles scattered in direction phi per second, or the scattering cross section, you can see this result is directly proportional to cosec 4 phi by 2. So you can see that the number of particles scattered per second in a particular direction strongly depends on that direction, because here there is power 4 on cosec, and so it is, you can say that it is strongly dependent on the angle of scattering. Okay. Again you can see this is also proportional to the square of the charge of the nucleus, that is Ze, and it is also proportional to a square of the charge on the particle, that is a small Ze, and it is inversely proportional to the square of the initial kinetic energy. You can see E is in the denominator. Okay. These are the factors which affect this differential scattering cross section, or the number of particles scattered per second in a particular direction of scattering. Okay. Now, if you represent by this symbol n phi the number of particles scattered in the direction of the angle phi per second, then you can write that n phi is equal to k times cosec 4 pi by 2. Here this k is actually a constant, or you can say apart from this cosec 4 pi by 2, the remaining factors is actually k. Okay. So we can also express this scattering cross section result in this term n phi, in terms of n phi, which represents the number of particles scattered in a particular direction phi. Okay. So you can see if the expression for the angle of scattering, or the impact parameter, and the differential scattering cross section is in your mind, which we have learnt in the first and second video, then you can easily find the expression for the differential scattering cross section. And on what factors this differential scattering cross section depends, you can find from that result. Okay. Now, actually, now I am giving you a very important example, or you can say very important problem we will solve here. This type of question will be asked in different competitive and university examination, and you can see how easily we can find it. Such a problem is also asked as a multiple choice question, but I have actually written here in the not in the form of MCQ, but as a problem. You can see the question says, determine the differential scattering cross section and the total scattering cross section for the scattering of a particle by a rigid elastic sphere. There is a rigid elastic sphere, a particle is incident on it, it suffers elastic collision, and you have to find what will be the differential scattering cross section and the total scattering cross section. Let us see the solution. Let us consider this is our sphere. This is elastic sphere. Okay. And A, I have assumed that A is its radius. And you can see this line, let us say XO. This line is actually the line of symmetry, because it is along the one of the diameters of this sphere, and we consider that there is a particle which strikes this sphere at a point B moving in a direction AB. Okay, this particle we have assumed is not moving along this line of symmetry. So you can say the perpendicular distance between this line of symmetry and the line of this incidence direction of the particle, which I have marked by P. This is impact parameter. Okay. So in accordance with this figure, you can say that BD is equal to P, and this is impact parameter. Okay. Now, the particle strikes the sphere at a point B. Okay. And since our problem says that the collision between this particle and the sphere is elastic, so after striking, the particle gets reflected or gets scattered in this direction BC. We have shown in this figure. So BC is the scattered direction of the particle. Okay. And this BC is the scattered direction. Okay. And this you can say AB is the incident direction. Actually, I have marked something here wrongly, so you can see. See here. Okay. This is the incidence direction. Okay. And this is the BC is, this point is B as I have marked. BC is the scattered direction. Okay. And you know the angle between the direction of incidence and the direction of scattering, this is angle of scattering. So you can say if we mark it by, let us say, A dashed, then the angle A dashed BC, this is equal to phi, and this is angle of scattering. Okay, this is angle of scattering. Now let us join this point B to the center of this sphere. Okay. As you know, the radius of the sphere will be normal to this point. So this OBN is the normal. Okay. OBN is what? This is normal at the point of incidence. Okay. Since the collision is elastic, so you know the angle of incidence, which is actually angle ABN, that will be equal to angle of reflection, because in elastic collision our particle follows the laws of reflection of light. So you can say angle ABN will be equal to angle CBN. Okay, both of these angle will be equal. Now again you can see angle ABC. Angle ABC will be what? See the figure. Angle ABC, ABC, this will be equal to what? This is pi minus pi, because this total angle will be pi. Okay, and this is pi. So ABC, angle ABC will be pi minus pi. But angle ABC is the sum of angle ABN and CBN, both are equal. So you can say that angle ABN, okay, and this will be equal to angle CBN, and this will be pi minus pi divided by 2. And so this is pi by 2 minus pi by 2. Pi by 2 minus pi by 2. Okay. Actually, I have calculated here wrongly, because you can see this is angle ABN and CBN, and this calculation is correct. Okay, but this is angle DOB. This is correct. But here in this figure, I have written this wrongly. Angle OBC, not OBC, but A dashed BC. This will be A dashed BC. A dashed BC. This is A dashed BC. Okay. Now see, now from this geometry of figure, you can find the impact parameter P. As you can see, this BD is equal to P. Now, since this line AB is parallel to the line XO and line ABN intersects both of them, then from elementary geometry you know that this angle ABN, this angle, will be equal to angle XOB, this angle, or you can say DOB. So this angle DOB is also equal to pi by 2 minus pi by 2. And so from this triangle, this point is actually B, BOD, we can find the value of impact parameter. You can see from that triangle, sine pi by 2 minus pi by 2 will be equal to P by A. This will be P, that is BD divided by OB. Okay, and so P is equal to this much, A sine pi by 2 minus pi by 2, and sine pi by 2 minus pi by 2 is cos pi by 2. So P is equal to A cos pi by 2. Okay, so we have obtained a relation between the impact parameter P and the angle of a scattering phi. But you know, for getting the value of differential scattering cross section, we must know dP by d phi. So now let us differentiate this P with respect to phi. You can see P is equal to A cos phi by 2. So dP by d phi, this will be minus A by 2 times sin phi by 2. Now this value of P and this value of dP by d phi, we will substitute in the standard equation of differential scattering cross section. As you know, the differential scattering cross section sigma phi is given by what? This is minus P by sin phi into dP by d phi. This is the standard expression. Okay, but you have seen that P is equal to A cos phi by 2. So at the place of P, I have substituted this. And sin phi by 2, which is in denominator, that can be written as 2 sin phi by 2 into cos phi by 2. And you have obtained just now this dP by d phi. What is this dP by d phi? You have seen this is actually equal to minus A by 2 into sin phi by 2. Here is minus sign. And in this expression, there is also minus sign. So those two minus will now become plus. So I have not written here minus sign. So this is A by 2 into sin phi by 2. Now see, this cos phi by 2 and cos phi by 2 will cancel out, and this sin phi by 2 and this sin phi by 2 will also cancel out, and so our result is sigma phi equal to A square by 4. And this is the expression for the differential scattering cross section of the scattering of this particle from this elastic sphere of radius A. And you can see the dimension of this sigma phi will be the dimension of A square, that is meter square, that is the dimension of area. Okay. Now, you can easily find what will be the total scattering cross section. As you know, the total scattering cross section denoted by this symbol sigma will be simply the integral of the differential scattering cross section. This d sigma by d omega, this is differential scattering cross section. So sigma is written as integral of d sigma by d omega d omega. And d sigma by d omega, this is sigma phi, and sigma phi you have obtained. This is A square by 4, which is constant. So let us bring it outside of the integral. So this will be A square by 4 integral of d omega. What is this integral of d omega? This is actually the total solid angle subtended by this sphere at its center. At its center. Here, its center is a scattering center. And you know, the total solid angle made by any closed surface, not a sphere, any closed surface at any interior point is equal to what? That is equal to 4 pi. Here you can easily calculate it. This integral d omega means omega, and this omega will be equal to a divided by r square. A divided, and a is area of this sphere. This will be 4 pi a square, and r means a here. So this will cancel out, and this is 4 pi. Okay. But in general, if instead of there will be any closed surface, and the point where solid angle is to be calculated is inside that closed surface, the total solid angle subtended by a closed surface at any internal point is equal to 4 pi. So I have substituted here 4 pi at the place of integral of d sigma. And you can see this 4 and 4 will cancel out, and sigma is equal to pi a square. This is a well-known result. Even when we deal the problem in quantum mechanical way, you will see some in the scattering process like NPS scattering, PPS scattering. This type of result is commonly occurs. Okay, and from here it can be seen that the dimension of this scattering cross section is the dimension of area. Okay, so this is a very important problem. Commonly this type of question will be asked as a multiple choice question, and you can see if the choice will be the total scattering cross section, if the choice will be 4 pi a square, 2 pi a square, pi a square, and nothing, then if you don't think seriously and if you not use the calculation, if you not solve the problem doing the proper calculation, you will think that the cross section should be 4 pi square, but this is not 4 pi square, this is only pi a square. Okay, so I think after these 3 lectures on scattering theory, or on the classical scattering theory, now definitely you have a concrete knowledge of classical theory of scattering, particularly this Rutherford scattering. Actually, this Rutherford scattering theory is very important for both the competitive examinations and also for the students of BSc honors and physics, BSc honors and MSc physics. Okay, so go through all these 3 videos on classical theory of scattering, note down these things in your notebook, and that will be a very good notes for you for your examination purpose. Okay, thank you very much.